There are some portions of the notes as we go along that you may just kind of have to add. All right, so we're going to start off by talking about periodic table, and then we'll get to periodic table trends. It's a pretty short unit, so we may actually be having a test over it by the end of next week or early part of the following week. So before Mendeleev, which was the scientist that was discussed in the little video that you watched, when he came along and started working on the periodic table, there were about 70 elements that were known, but they weren't really arranged in any way that was of any use to anybody. So there was it would be a really big deal or very hard to get information about those different elements. So he arranged them into what was called the periodic table, which we know is now a very useful tool for all chemists. And like y'all get to use it on every one of your tests. And it takes that information that he had and other elements as they came along and puts them in a way that makes them predictable as far as their behavior. I think I might have jumped ahead of myself, kind of already said some of these things. A lot of information before the periodic table, but hard to access. So then we have good old Mendeleev came along, that was able to go to school thanks to his mother, you saw from the video. So he's considered the father of the periodic table. And he put the elements in rows by increasing atomic weight. So I think that is your first blank under Mendeleev. Increasing atomic weight or increasing atomic mass is how he worked with the periodic table. And then he put elements in columns, which eventually became groups that reacted in a similar way, like Jenna said. There were problems with some of the things after he created his periodic table. He actually left blanks in his periodic table for where he thought undiscovered elements would eventually be discovered. And from the video, you found out that he was right about that. And he broke that pattern of just putting them by increasing atomic weight, because he also wanted to put elements that reacted similar together. So like everything in group 1, because they were very reactive metals. And that wasn't possible if he kept them just by increasing atomic weight. So he did have to make some adjustments. So eventually Moseley came along, Henry Moseley, and he took what Mendeleev had done. He changed it around a little bit. And he instead took the elements and he arranged them by increasing atomic number, which we know is the number of protons. So the periodic table, which we still use today, is based on the order of atomic number of the elements. And the periodic law, which is the law that's followed in regard to the periodic table, says that physical and chemical properties of the elements are periodic functions of their atomic number. So in other words, with these scientists, it wasn't just the matter that they put them in order according to atomic number, atomic mass. They had to figure out how many groups they needed so that that periodicity could be seen. So if he wanted the most reactive metals in group 1, then they had to figure out how many groups that they had until he needed to have another group 1 metal placed. So that's what periodicity is. When they line up, and when they line up, they're going to have similar chemical and physical properties. So the periodic table is arranged so that atomic numbers of elements with similar properties fall in the same common column or the same group. The horizontal rows, we have 1 through 7. Those are called periods. And the vertical columns are called the groups, 1 through 18. It's within a group that you see similarities in properties. So in other words, if I'm talking about potassium, which is element number 19 in group 1, and I asked you to give me an element that was similar to it in regard to property, you would want to pick another element, not hydrogen because it's not a metal, but another element out of group 1. You wouldn't want to pick something in the same period within that element. You see similar properties within a group much more than you do within a period. So like I kind of mentioned before, periodicity is a similarity of the elements in the same group, and it's explained by the electron configuration, or the way that the electrons are arranged around the nucleus, especially the valence electrons. So groups within the periodic table are very useful. And like I said, a couple of reasons why we see similar properties. One is that they have the same number of valence electrons within a group. And valence electrons are especially important with regard to reactivity of elements and how they are going to form bonds, or what types of bonds they're going to form. And then also within a group, you see the fact that they will form the same kind of ion, which is what we'll be looking at tomorrow. And once again, this was not just random that we ended up with 18 groups. It was planned by the scientists that organized the periodic table. Also, sometimes you'll see different families in the periodic table, and we're going to talk more about some of the families. We don't really deal with those nearly as much as the groups or periods, but a family may be made up of one group or may be made up of several groups. So for instance, the transition metals, those could be considered a family. Let's go metal. Remember, transition metals or anything from group 3 through 12. That would be an example of a family. It doesn't involve just one group. And they kind of have some general name that covers all of them. And like I said, we'll name a few more in a little bit. We have hydrogen, which is element number 1, and helium, which is element number 2. And they're considered kind of oddballs because of the groups that they're in. They don't exactly follow the rules of some of the other elements that are in that group. So hydrogen belongs to its own family. It's in group 1, so it only has one valence electron. To shorthand valence electron, I just put VAL and then electron symbol. It is a diatomic gas. It's very reactive. When the Hindenburg blip blew up, it was because they had filled it with hydrogen gas. And it's in group 1. It's not a metal, so it's not part of the alkali metals. But we'll find out everything in group 1 has one valence electron, and that's why it's put in that particular group, because of its electron configuration. And then across the board, we have helium, which is another little oddball. I don't think I have a slide for it. It seems to have gotten lost. Oh, where to go from group 2? Jumped all the way to group 2. There was a little helium slide just there. All right, so if you see helium, it's under there under hydrogen. It's in group 18. It is a noble gas because it is unreactive, but it does not have valence electrons. Every other noble gas has 8 valence electrons. Helium only has 2, but it is stable with just those 2 valence electrons. So it is very unreactive, and it's a gas, and that's why it's put in that particular group, even though its electron configuration is a little bit different. All right, then we have group 1, our alkaline metals. So these are our most reactive metals. They are S block elements. That has to do with their electron configuration. They have 1 valence electron. That's what makes them very reactive. They're so reactive that they won't be found just by themselves in nature. They have to be combined with something else. They end in what's called the NS1 configuration. That has to do with their electron configuration, and N is what period they are in. So like lithium would be 2S1. If you come down, sodium, it's at period 3, so it would be 3S1. Their reactivity increases down the group. So in other words, as you move down, they're going to get more reactive. And this is actually true for metals. And the reason that is that as you move down, the elements get larger, and the electrons, valence electrons get farther from the nucleus. So it's easier to lose those valence electrons, and that's what makes them more reactive as you go down your group. All right, then we have group 2, which are our alkaline earth metals. They're still very reactive. They are also S block elements, and they have 2 valence electrons. A little bit less reactive than group 1. Has some nutrients like magnesium, calcium that fall in that group. And the same thing as group 1, their reactivity increases down the group because they're still a group of metals. All right, then we'll move on across the periodic table to groups 13 through 12, which are the transition metals. These are D block. So these were like our classic metals. You know, I don't know about you, but when I think of potassium, I don't think of metal. I think of a mineral that you need. Same thing for calcium. But within these transitions, it is the metals that we think of, like silver and gold and copper and platinum and all of those. They fall within there. They're less reactive, and they have those classic metal properties that we'll talk about in a minute. I know y'all have heard about them. This is where the things that we like to make jewelry out of, because they're shiny, fall in there. As far as their valence electrons, it differs a little bit. It's not a set pattern, so it could change up. We don't spend a lot of time on transition metals in Chem 1. That in AP chemistry, we would spend a little bit more time on that. All right, so then let's talk a little bit about the metallic properties to refresh your memory, because I know y'all have heard of all of these before. Malleability is the ability to hammer the element into sheets. Ductility is to be able to pull that element into a wire, like copper wiring. Luster is shiny. That's why we like to make jewelry out of it. And then they're good conductors of both heat or cold and electricity. All right, then we're going to move across to group 13 through 18, which are very predictable, like group 1 and 2. So we do spend time on those. So we'll start with group 13. It's a P block group. In fact, everything from 13 through 18 is a P block group. Group 13 in particular contains some metals, some nonmetals, and some metalloids. And the metalloids, like we talked about earlier, are on that stair step. And they are going to have properties of both metals and non-metals. So they're semi-good conductors, not quite as good conductors as the transition metals. So group 13 itself has 3 valence electrons. When you move over to group 13 through 8 to find out how many valence electrons it has, you would take the group number and subtract 10, and that tells you how many valence electrons it has. And you'll see tomorrow with ions that becomes important as far as predicting what kind of ion they will form. All right, so these different little families, there's a few of them that are mentioned. You'll kind of have to add them onto your notes. Group 13, which starts with boron, is called the boron family. It has aluminum within it, which we think of as a disposable metal. It used to be thought of as a rare or a precious metal. Now, there's a lot of things cheaply made out of aluminum. The next one, the next family, it's going to be the carbon family. Group 14 starts with carbon. Not real original with these names here. So we know carbon is very important for life. Something that contains carbon is an organic compound. I know you remember that from biology. So that includes many living things. Carbon is an element that tends to share electrons and form instead of forming an ion. And because of that, it behaves very differently than a lot of other elements. So that's why there is an entire branch of chemistry devoted just for compounds containing carbon, and it's called organic chemistry. And those of you that are going into medical fields, some engineering, some other things, you'll have to take organic chemistry when you get to college. Most people find it pretty hard. Then, once again, not very original. Group 15 starts with nitrogen, so it's the nitrogen family. Probably most important element in there is nitrogen because it makes up about 75% of our atmosphere, even though it's not available until it's fixed. If y'all remember that from biology, which is something some bacteria that do in legumes, change it into a form that can be used by living organisms. Then we have group 16. Anybody want to guess what group 16 is called in regard to the family? Yes, it's the oxygen family. Or the Chalcogens. I don't even know really what that means. I meant to look it up. So it has oxygen, which we know that we need to have to breathe with. Sulfur, which is very stinky. Have any of y'all ever been around a sulfur plant? Yeah, it smells like rotten egg. So if you have food that kind of smells that way, it's probably because they contain sulfur. Let's see if I can find out why. Doesn't really say why. I guess it's a different language. Is all I can see. So don't really see why it has that name. All right, let's get to something that we'll actually be spending time with. Group 17 is your halogens. So these are our very reactive, our most reactive non-metal group. They have 7 valence electrons. They need one more, and that's what makes them so reactive. They're trying to grab them from group 1 or group 2. If you look at them starting with iodine all the way up, they have over half of the diatomics within that group. You have your iodine, your bromine, chlorine, and fluorine. So that's 4 of the 7. Their reactivity increases as you go up the periodic table. So it's opposite of the metals. So fluorine would be my most reactive non-metal. And that little trend is true for non-metals. It's opposite of the metals. And that's because non-metals are trying to hold on to their electrons. So the closer they are to the nucleus, the more easy it is for them to grab another electron to get their full octet. And then last but not least, as far as group go, we have our good old noble gases. So group 18 would be our noble gases, called that because they don't want to react with anything. They want to just be by themselves. I guess that's how nobility would want to be. They're very unreactive and they're monoatomic gases, meaning they can be stable as just one atom. On this periodic table in our classroom, everything that is red is a gas at room temperature. So all noble gases at room temperature are red. They have a full valence, which would be 8 valence electrons, and that's called an octet. And that's what makes them so stable. It's the octet rule. The exception is helium. It doesn't have 8, it only has 2, but it is still stable with 2 because it's so small. So we'll find tomorrow that as these different elements either take electrons or give away electrons, the whole reason that they would do that is because they're trying to get to this octet of valence electrons that leads to stability. All right, last 2 little things on the next page are these pulled out elements. And the only reason they are pulled out of the periodic table is because if you try to fit them in there, it makes the periodic table very, very long. So the first line is called the lanthanides, shiny reactive metals, and these are F block metals. And then the next one, actinides, and those are where we see the radioactive elements. They're unstable. So like uranium falls in there. All right. So we're going to stop there. It's a good place to stop. We're going to watch a little video. Tomorrow we'll do ions, and then we'll probably come back to these notes on maybe on Monday. Y'all have a quiz tomorrow over the portion of the notes that we've covered so far. So quiz tomorrow over the portion of the notes we've covered. All right, let me get out of here. That's up real quick, and then I'll get the video. Video. That's not what I wanted. Here we go. So this is looking at that group 1 metal.
When you've left school, you're still at school. You can appreciate the sheer fun, mayhem that chemistry can make. There's so much to it. Buzz and bursts, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. Odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, my present. These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Right, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody, this one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone.
We won't be doing that aloud.
That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There's one more alkali metal we can use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty to go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Brandon, mate, I'll be good luck.
Thank you.
Okay, John, go for it.
Warning, extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, frankium. But for some reason, they wouldn't let us have any of that. Except, there you go. Today's lesson.
Never mixed alkali metals with water.
So I've got my essay written, and I've been working on it for about a week. So now
So
I'm going to
did-
show you how I use Grammarly to edit.
On the video from last night,
And I'm going to click through Grammarly suggestions.
did anybody catch, it was said pretty quickly, but did anybody catch what they said the group 1 metals were stored in? Very specific conditions. So since they're reactive in water, what do you think they might be, what liquid do you think they might be stored in? It's actually, they store them in oil because they're not reactive in oil. So they're stored in oil to keep their reactivity. We really don't keep those kind of things in our lab because, but it's interesting, you know, sodium's that reactive, but then if you combine it with chloride, and chloride's very reactive, but then if you put them together, you get table salt, which obviously isn't reactive at all. And that's because they formed that compound to do that, to become much more stable. So this one looks at the different metallic properties.
Hello everyone. Today we will discuss about the properties of metals. At the end of this video, you should be able to describe list of metals. So watch and listen carefully. Let's start the video.
What makes a metal a metal? Here are the properties of metals. Number 1, luster. Number 2, ductility. Number 3, malleability. Number 4, magneticity, the shiny
We'll
appearance.
see, this
of
one looks kind of
metals.
boring, y'all.
The ability of metal to allow heat
Okay.
to pass through it.
Let's do that one for this. It's a little boring. All righty. I think we will. call it a day. I'll try to find a better one for the different properties. That one.